My name is Michał Jamroż. Here is my colleague Matthew Opala. We are both co-founders and data scientists in Craftinity company. Craftinity is a startup from Krakow doing machine learning, deep learning in particular, and we aim to solve problems. And using these techniques, we aim to solve problems emerging in industry. Okay, the title of our today's talk is Representation Learning, and let's take a look at what we are going to talk about today. First, we will describe very briefly artificial intelligence, machine learning. We'll give some goals of doing it. Later, we will give a general overview of the representation learning. We'll present some cases for the need of doing this. Later, we will move to deep architectures being the core of deep learning. And finally, we will show some examples of representation learning of different types of objects like text and text and images. Okay, so first, very briefly about artificial intelligence. What's the goal of artificial intelligence? Its main goal is to build an intelligent machine. And the goal of the intelligent machine is to make good decisions. And just like humans, in order to make good decisions, the machine needs some knowledge. And because the knowledge is very difficult, almost impossible to verbalize explicitly, it cannot be conveyed by the programmer to the program, but it needs to be learned from the data. It needs to gain some experience, see some examples, and learn this knowledge from the data. And general machine learning is essentially about generalizing the observed examples for the unseen data. Yeah. And okay. And when we perform machine learning tasks, we perform them on object taken from the real world, and they need to be somehow represented. And later, we need to be represented in the computer's memory in form of vectors or matrices. But later, we need to extract some meaningful features from those raw data, and it's crucial to extract good features in order to have a good performance of machine learning algorithms on different tasks. And there are two possibilities of having features extracted from the raw data. The first one is feature engineering doing by hand. It consists of the situation that there is a human which takes this raw data and tries to decide which things matters here and which things don't matter and needs to be thrown away. And on the other hand, automatic learning of the feature is essentially that we want the machine to do this task, that is discover automatically which things in those data are meaningful. Okay, let's take a look at how things look in machine learning in industry nowadays. It appears that most of the time of doing machine learning on some problems, most of the time is spent on manual feature extraction. It's even 90% of the whole time to do the manual feature extraction. It's not about improving machine learning algorithms, but rather verifying which set of features gives better performance, gives better results. And obviously, we would like to have the pipeline looking like this one in the bottom. We would like to have the process of feature extraction included in the machine learning. Okay, and let's find out why we should do the representation learning. The first thing is apparent from the previous slide. It's very time-consuming, it's incomplete, it's prone for human errors. But the next thing is that it brings the ability, so to speak, to do the unsupervised feature learning. Unsupervised learning is a type of learning where there is no additional information associated with the data. We just have only the raw data. And why is it a good thing to do? At first, data which we collect from the outside, for instance, from web, are mostly unlabeled. And relying only on those data which have some kind of information, additional information like labels, causes that our data sets are relatively small, and it's always a bad thing to have less than more data in our data sets. What's more, labels do not provide enough information. It's necessary for us to discover the knowledge lying in the raw data without any relation to those labels they have. And what's more, unsupervised feature learning is somehow generic. We can learn knowledge from the raw data and later use it in any task, in any machine learning task we have to do, whether it's classification, regression, or clustering. Okay, the unsupervised feature learning is very strictly related to so-called semi-supervised and transfer learning, which are relatively new types of learning in machine learning area. Transfer learning consists of learning the knowledge from the data by performing some task and later use it to perform the other machine learning tasks. So it's somehow transferring the knowledge gained during performing the previous task to the next one. And semi-supervised learning is type of learning when our data set is partially labeled, both labeled and unlabeled. And because, as I said, the data collected from the outside are mostly unlabeled, it usually happens that the size of the unlabeled data set is much bigger. Okay, the data representation can be composed into hierarchy, which makes the architecture deep, and more about deep architecture will be taught by Matthew.
Okay, so before I start, I have a couple questions. Who knows deep learning here? Oh, quite good. Okay, so who knows classical neural networks? Even better. Okay, so I will try to give some reasons why do we need deep architectures. Do we need them? And firstly, let's start with some theoretical work. And actually, almost 30 years ago, it was discovered that there are some families of functions which can be represented compactly by k-layers architectures and cannot be represented compactly by k-1 layers of architectures. And what does it mean compactly? Compactly means that representation is the number of latent variables in architecture is polynomial with respect to the input size. So if we cannot represent some function compactly, then we need to have exponential number of hidden layers, of hidden units, which is usually very impractical and time-consuming to compute. And actually, very interesting is that any Boolean functions which are quite simple to represent in computers, can be represented by a single hidden layer, but sometimes it could require exponential number of hidden units. And this works for XOR function, and it was shown by Minkowski in 1969, because neural nets started in the mid of 60s, early 60s, but by Frank Rosenblatt, who discovered perceptron. And in 1969, Minsky wrote the great paper about limitations of perceptrons, and showed that even XOR function, which is quite easy to represent in computer, its perceptron cannot represent the XOR function, having only one layer. So let's move on. Yeah. So that's another formal example. So this is parity, d-bit parity function, which is just taking some number in bit representation, and it's equals to 1 if the number of ones is even, and it's equal to 0 if the number of ones is odd. And it was shown by Yao in 1985 that it cannot be represented with a polynomial number of units with just one single hidden layer, and later was generalized to multi-layer perceptrons with linear threshold units. So this is quite easier task than usual AI tasks like recognizing faces or images or learning totally unsupervised the text meaning. And still we have a proof that we cannot do this with shallow architectures. So it strongly suggests that if we want to do AI tasks, we need deeper architectures. So let's maybe catch some intuition about this. So how deep representation do we need? So 5 layers. Anybody? No. Okay, you don't want to play this. And it's right, because it's data dependent. So usually most of people agrees that when you have 2 layers, 2 hidden layers, it's deep. But the father of deep learning, Yoshua Bengio from University of Montreal, says that it's totally data dependent. So even if you have one single hidden layer, but it can represent your data. And actually we will see the example of understanding the text when you have only one hidden layer and it works pretty well. Then your architecture is deep. Okay, yeah. Okay, so let's take analogy from programming, because probably most of people here are software engineers and probably everybody's coding in Python, which is pretty awesome language, object-oriented programming, object-oriented and also with some functional features. Yeah. So usually when you code, you don't do this like that. You don't write shallow programs. You don't repeat yourself. And it's very good. But like 30 years ago, people were coding in Fortran, and especially machine learning scientists. They were coding very shallow programs, and they still actually. And if you read their MATLAB code, it's horrible. So I prefer Python definitely, and software engineers. So the idea for deep learning, maybe the analogy for deep learning is taken from software engineering, that the same like in software engineering, we want to have some modularities. So when you look at your project, at your IDE, you see the tree structure and packages and modules and then classes and mixins and something so on. And you can reuse this code. So the idea is to do the same with architectures of machine learning models, with architectures of neural nets. Yeah. So usually nowadays programs look more like that. And that's pretty good because we can reuse this code. It's easier to read, easier to write. Easier to read is very important. So we want the same thing in neural nets, reusing. So we want that one neuron can transfer its knowledge to the other one in higher layer, so the other one can learn more abstract concepts. And we will see example just in a second. So let's go on. So this is also, we have also inspiration from biology. in 1962, there was a great paper about from Hubel, and he figured out how visual cortex is working. And actually, it's working. It's not just recognizing the objects, but first, there are several steps. And first, we are recognizing some strokes, some edges, then some surfaces like ears, eyes, and lips, and then we just recognize the whole face. So we would like to do the same with neural nets, because everybody wants to imitate human and do the strong AI, which we are really far away from that, but let's try it. So I'm not sure if you see it, but these are results from 2009 from Convolutional Deep Belief Network. And these are visualizations of filters of neural net, which are, when you compare to the brain, there are just synapses in brain. So when you visualize them, in the first layers, you have strokes and edges, and they are not here. But the next layers, you have some shapes, like for faces, you have eyes, ears, nose. For cars, you have some parts of cars. And even when you train your net to recognize more objects, like faces, cars, airplanes, and motorbikes, there are some filters which are, there is nose and there is some part of car. And in the last layers, there are just whole faces, whole cars. And so this is really strong assumption that we can do deep learning, similar that brain is doing visualizing things. So this is pretty impressive, actually, result. So let's go on. Okay, that's also another one example. So I'm sorry, Dave, I'm afraid I can do that, and let's get back. Okay. And probably everybody can paraphrase this, because probably everybody can speak English, and we have built the higher level representation, and we have some abstract, higher, more abstract concepts of English language in our mind. So we can just paraphrase, and I don't remember right now the sentence, but I can say that, hey dude, I can do that, whatever. And the meaning is the same. But let's go, yeah, and let's get back. And no way, unless somebody knows Chinese. Actually, it's also the same sentence, but we don't have, if we didn't learn Chinese, we don't have this high-level representation. So we cannot just paraphrase easily. If I want to type this sentence in Chinese, can you go back there? Yeah. If I want to type down this sentence in Chinese, again, I would have to go stroke by stroke, and probably it would take me 30 minutes, and I would have mistaken, obviously. Yeah. So there is the intuition that we need deep representation, because there are some formal arguments, really strong. But usually machine learning scientists, which are against deep learning, they're always saying that there is not much theoretical proofs about deep learning. And for part of deep learning, it's true, but it's working. So that's the most important thing in industry. Yes. So let's go later. So let's build the deep representation. So probably most of you know multi-layer perceptron, which is just classical neural net feed-forward. It has input layer, several hidden layers, and output layer. And usually, if we're doing classification, we just learn some probabilities of some classes in the last layer, optimizing some function like cross entropy to make the probabilistic distribution of our data, of labels of our data, similar to the real ones, to the targets. Yeah. So just quick reminder how we do the learning in classical nets and actually everywhere. So usually we use gradient-based methods, and so we have to compute the gradient, which are just the vector derivatives with respect to the parameters of the net. And then we can do the gradient descent, which is just going with the step of the gradient in negative direction, and just try to get into the local optimum of the cost function or objective function or so on. Yeah, but multi-layer perceptrons, people didn't use them in 90s. So they have problems. And one of the problems were vanishing and exploding gradients. So because when the architecture is very deep and computing the gradient, usually we use backpropagation algorithm, which is just the chain rule from the analysis. So when we compute the error of the last layer and then we are propagating this down, so if the norm of the weights is big, it can explode. If it's very small, it can vanish. And it's the same problem with recurrent neural nets, actually. So that was one of the big problems. The other one was stacking in poor local optima, because usually the cost function is very highly curved, and when you start from the totally random initialization, it's very easy to get into local optima, especially with gradient descent, which has no features to prevent this. So the next thing is lack of good initializations. It's also the cause of the stacking in poor local optima. There is also lack of labeled data. Just in last year, we produce like 90% or 95% of all data we have right now, but all of this data is unlabeled. So we don't have any answers that on this image there is a cat or a dog. And we would like to use this data because there is so much data and not so much labeled data, but multi-layer perceptron requires labeled data. And in 90s, we didn't have much labeled data. We still don't have much labeled data, but in 90s it was definitely worse. And multi-layer perceptrons didn't work, and because a whole buzz about neural nets started in 1960s, so it took like 30 years, and they weren't working well, actually, unless you are French and use convolutional neural nets, because Jan LeCun was French, and he actually did the recognizing the bank accounts from the checks, and it worked in US, but only for French people. So there was very hard time for researchers to encourage people to do the PhD in neural nets. So there wasn't much research because there wasn't much PhDs, and the hardware was very slow in comparison to nowadays. Yeah, but there was a breakthrough. And that's the reason we are talking today about deep learning. So in 2006, these three guys, from the left, Jan LeCun, the French guy from convolutional neural nets. He's from NYC in New York City, currently in Facebook. Geoffrey Hinton from Toronto, currently in Google, and Yoshua Bengio, currently still in academia. And they discovered the way to pre-train neural nets so they have better initialization to start, so you don't stack in poor local optima, and also the hardware was better at the time. So we fixed some problems. So let's go on. So the way they fixed it, it was greedy layer-wise pre-training. So they took the shallow net, which is restricted Boltzmann machine. This is probabilistic graphical model, but it's also a stochastic neural net, and RBM, what RBM does? RBM models the probability of observed data. But this probability, when you try to compute it, it's intractable because you have to consider all configurations, all possible, because of partition function. So, but we can infer conditional probabilities for visible layer given hidden layer and the other way. And using this, they discovered that we could approximate the gradient of negative log likelihood, which we usually want to optimize in that case. So that was the great way to train restricted Boltzmann machines. And they could be trained fully unsupervised, because what we are doing, we're just optimizing the probability of the data, of the observed data. So we don't need any labels, and we can use all of this data which is unlabeled, just scroll the internet and use it. And the next thing which they discovered, that actually when we stack RBM, so we train the first RBM, so it can reconstruct the data very well, and then give the output of the first RBM to the second one as an input, and train the second one, it's working even better. And we can add this, and it's going to work better, and better, actually. At some point, the change is very small, so there is no point of adding, because it's also time for computing. But there is theoretical proof that adding more layers or adding more units is always better, or it's not worse. It's not worse, actually. It cannot be worse. Yeah. So so that was a breakthrough. But with RBMs, of course, RBMs are great. We can do the semantic hashing. So something like Google image search could be done with RBMs. We can analyze text. We can do the recommender systems with RBMs. And there are actually classes of RBMs which are temporal. So we can model some dependence between some random variables. So it's like recurrent net. But there are some limitations. Because for natural images, we would like our model to be invariant to some transformations, affine transformations, which doesn't change the label of the data. So we would like to be invariant to translations, rotations, maybe stretching, and fully connected networks do not introduce such invariance. So we need something else, and actually we have this convolutional neural nets, which Jan LeCun used in 90s, and it was only neural net which was working at the time, and only for French. So convolution is the main operation for a convolutional neural net, and it introduces the sparse connectivity and parameter sharing. And let's talk about it. So the sparse connectivity means that in RBM or perceptron or multilayer perceptron, all visible units are connected to all hidden units. But here in convolutional nets, the connections are sparse. So when we take one visible unit, it's only connected to a couple of hidden units. And this introduces the sparse correlation between neurons of adjacent layers. So what does it mean? So when we have this analogy with visual cortex, that in the first layer we learn strokes and edges, and later we learn some surfaces. The sparse connectivity, it's something that promotes this, because sparse connectivity promotes learning something local. And firstly, we just learn edges and strokes. But then after convolution, feature maps are smaller, and we learn surfaces and so on. And the second one is parameter sharing, which introduces invariance, because all of the filters are shared through all neurons, so we can detect the same feature in every place of the image. So this is invariance for translation, which is pretty awesome, actually. So how does convolution work? And why does it not work in a GIF? But I don't know. OK, whatever. So we are just going with sliding window through the image. And we have some filter, which is the yellow square is a filter. And the green one is the image. And it should move, but it doesn't. I don't know why. So we are going with the sliding window and multiplying the window with the window of the image with the filter element-wise, and then sum up all elements. So and then put this in convolved feature map, and we got 4. And then of course we apply some activation function like logistic function like sigmoid, or usually in convolutional neural nets we use rectified linear units, which makes great improvement for them and speed up the training process. Yeah. Okay, so the other operation which is usually used in convolutional neural nets is pooling. And pooling is just downsampling. So we're taking the window of size maybe 2 by 2, and then we're just taking the maximum or average of this window and put to the smaller feature map. So we're just reducing the size of the feature map by some factor. And pooling introduces local invariance to local translations, whereas convolution introduces global invariance to translations. Okay, so this is the architecture of AlexNet from 2012, and it was like a big step in deep learning, because there is this great ImageNet competition, and all companies are always competing in this, and even this year Baidu was cheating, and they cannot compete next year. No, Craftinity is not competing, unfortunately. Maybe next year, we'll see. So there is this great competition, and everybody had some solutions, and but it was definitely worse than human. The problem was we had like very big data set of images, natural images, and we had 1,000.
Thousands of millions.
Yeah, a few dozen of millions images and 1,000 of classes, right? Yeah. So we have like 1,000 of classes. You need to classify these objects, and there are two metrics like just one hit accuracy and top 5. So what they did, they put the convolutional neural net doing convolution, max pooling, convolution, max pooling, and a different thing, because usually people were doing just convolution, max pooling, and so on, and they finished. But they do 2 convolutions, one after another. So because pooling operation lose much information, actually, and Jeffrey Hinton actually hates pooling, and he thinks that the brain cannot work with pooling. But it's Jeffrey Hinton. So they built this convolutional neural net with 7 layers, and it surpassed the state of the art at the time about 20%. So it's very much. And this year, actually, Microsoft doing some nice magic with math, improve human in some rates. Yeah, by using better activations of neurons. Yeah, so this is like common architecture of convolutional neural net.
Analyzed some models belonging to deep learning family, and right now we will move to the final point of examples of representation learning. And the first example will be the representation learning with text. And I will briefly describe word2vec and extension doc2vec algorithm. Both algorithms were invented by Tomasz Mikołaj with collaborators during his work in Google in 2013. And it aims to embed words and documents, in the case of doc2vec, in vectorial space. The size of this vectorial space is usually from a few dozens to a few hundreds. And it's actually not a monolithic algorithm, but rather it comprises some subroutines, but it doesn't matter here. Okay, from the architectural point of view, it's just the neural network with one hidden layer. And because neural networks has its parameters that needs to be learned from the data, word2vec and doc2vec also need to be trained. And this training is performed in purely unsupervised way. The only thing it needs is just the sequence of words. It doesn't need any labels and stuff like this. And the representation for the word or from the document is obtained by computing the hidden activation of this network. We just pass one hot encoded vector representing word or document and obtain its vectorial representation embedded in vectorial space. I told that it's a neural network, and let's take a look at this architecture. Explaining word2vec would be quite time-consuming, and there is also some math associated with it, mainly associated with the objective function used during training. So I'm not going through this, but I strongly encourage you to consult the paper, which title is Word2vec Explained, because the paper written by Tomasz Mikołaj is somehow cryptic, and it's not only my opinion. So it's very good to consult this paper, accessible via the URL at the bottom. Okay, but the essential thing about training word2vec is the objective function aims to predict the given word taken from the text, predict that the given word taken from the text appears in the context of some contextual words. These contextual words are typically the surrounding of this given word, and in mathematical sense, it tries to maximize the conditional probability of the word given its context, and it aims to maximize its probability through this whole data set. Okay, it would be everything about theoretical aspect of word2vec. Now I'm gonna describe some experiments which we performed with doc2vec. Okay, the doc2vec, I told that doc2vec is a slight extension of word2vec. What's the difference? Because doc2vec aims to find the representation not only for words but also for the document. So with this words from the context, we also pass to the network the vector identifying the document. So it also takes a look at the document these contextual words come from. Okay, so let's now talk about the experiments. Our problem was as follows. Our text corpus comprised 180,000 documents, and those documents were actually reports made by American companies, and they describe their activity in given fiscal year. And because companies operate obviously in different industries, there were some obviously those companies operate in those industry, and among these 180,000 documents, we also have about 9,000 documents which had explicit labels. That is, we knew in which industry the company which prepared the report operated into. And our task was to classify the remaining part of the documents. That is classified 170,000 documents. And by the way, it's a perfect example of semi-supervised learning mentioned at the beginning. Okay.
Is there any Python implementation?
Yeah. Obviously, we use the Python implementation provided by Gensim. It's accessible via pip and works pretty fast. Because obviously, the most time-consuming part of working with doc2vec is to train it on the text corpus, and training it at this amount of documents took us about 12 hours.
Can we train the algorithm incrementally? Like, if you have some new data, like 200 documents, do you need to restart everything from scratch? Or?
Yeah, we need to restart everything from scratch.
Actually, no. I mean, we can do like something like transfer learning.
Yeah, but
we need
there are
to
lags.
make sure that the distribution is
We have every word in the vocabulary. Yeah.
Ah, okay.
That's the other thing.
If you want to add one document, you need to train another.
Unfortunately, yes, but
model again.
I think that it could be achieved by implementing it properly. But as I know, there is no.
At the beginning with vocabulary, because if we doesn't have words from the new document in our vocabulary, then we have problem.
Yeah.
We have, we know.
Actually, you can just hash every word to do some subspace of, let's say, a couple of billions, and you can just hashing trick
That's right.
makes it work, I think.
Okay, but let's move on. Okay, before I will show you, because we will show you the accuracy and the performance of the classification on this representation obtained from doc2vec. It's worth to take a look at the representation of the documents belonging to sample different classes. Yeah, remember that we have a quite small label data set, and I would like to show you how does the representation of documents belonging to different classes looks like. And because we took the size of the vector representing the document to be 400, and we would like to be able to visualize it in coordinate system, we use the TSNE algorithm to reduce its dimensionality to 2. Okay, and let's take a look at the picture. It's actually how it looks like. It's very important to mention that the metric which measures the similarity between documents is not the Euclidean metric, but the cosine metric. So it measures the angle between the cosine of the angle between 2 points. And the more documents are similar, their cosine similarity gets closer to 1. So if we okay, so in terms of cosine metric, okay, if we draw lines here, here, and here, it's clear that this representation is very well separable in terms of cosine metric. That is, documents belonging to the same class lies quite close to themselves by the means of the angle. Yes, so it's apparent that our representation for the documents obtained from doc2vec is pretty well, and on this representation,
fully unsupervised.
Yeah, what's very important to mention, it was trained fully unsupervised. We didn't leverage this label set in this moment.
Did you remove stop words, so-called stop words?
Yeah, as I remember, we removed some.
But actually, you don't have to.
Yeah, you don't have to. That's a great advantage of Word2Vec, that you don't have to do many initial text processing. Yeah, like stemming
So
and
it doesn't
so on.
make any difference if you do the classification with stop words or without.
As we know, it shouldn't be, but in our case, we removed the stop words. But we don't know if it was necessary. Okay, and let's take a look at the accuracy of classification performed on this representation from doc2vec. Because our label dataset comprised only 9,000 of documents, we divided it to training and test data with ratio you can see on the slide. So our test set had about 2,700 examples. And remember that the number of classes the document can be assigned is 260. And we took some classifiers, standard classifiers like KNN with cosine metric in this case, SVM, binary SVM, but performing multi-class classification with 1 versus 1 approach, and random forest classifier. And as you can see, the performance of the classification on this test set is more than 80%. The best was KNN, 85%. So considering that the number of possible classes is really big, we can consider this results as very nice. But such a performance is so good only because of the great representation from doc2vec. So it doesn't matter what classifier we use, but it's not.
Actually, when we use just the bag of words on these classifiers, it was like 50%. So
15.
15. Yeah.
Uh-huh.
Yeah.
Yeah. Okay, and it would be everything about doc2vec, and right now we move to the next example, presentation learning on images and its styles.
Yeah, so let's talk about CNNs again, convolutional neural nets, which are awesome, and let's talk about the style and the content, because in the case of the text, we are learning some representation of the meaning, and we can, when we talk about AlexNet, we're just trying to classify some images. So we are building the good representation of these images, so we have good features and we can easily separate them. But is it possible to separate the representation of the style and representation of the content? Because for human it's possible. When we look at some Pablo Picasso picture, we can separate the style and we still see some human there, for instance. But probably it's very hard for neural nets, but not impossible. So let's go on. So we have this artwork from Matisse, yeah, from early 20th century. And next one, we have the picture of our CEO. And this is the content. So we would like to create an image which would Matisse draw when he wants to represent our CEO. So let's try it. Okay, so we start with this image, and we start to generate from this image, given that input images for convolutional neural net, to generate the image of our CEO in Matisse style. So the first thing we have to do is pre-training convolutional neural net. We need to already go back, represent natural images very well. So what we can do is just take the AlexNet or pre-trained weights, which you can find on Cafe Model Zoo, or you can also find on Lasagne, and I will talk a little bit later about this. Actually, in this case, we used VGG network, which is from the whole name of the network is very deep network because it has 19 layers. At first we have to define some object functions because we need to do some learning, so we need to know what we are going to optimize, what we are going to minimize. So as in the example from the paper from 2009 with convolutional deep belief nets, we saw that in the higher layers of deep architecture, we have pretty good representation of faces or dogs or something. So we need to optimize to reconstruct content very well. So the idea is to just take the root mean squared error in some higher layer, and actually we will take the one layer before last one, because the last one layer could be much data dependent, could be much labels dependent on the case where we pre-trained, and the features below should represent probably a little bit better the content of the image. We do believe this. So we just take this root mean squared error, and we have to figure out the R-slave representation. So G matrix is just the inner product of feature map. So when you do the convolution with filter, then you get feature map, and after each convolution you have feature maps, and this is just the next layer in convolutional neural net. And to represent the style, we just sum up all these inner products of feature maps, because we don't need special information for style, and we just compute the root mean squared error for style, like this. And we take it for all the layers. And the total objective function is the content loss function and the style loss function. So P is the original image with our CEO, and X is just the white noise, and A is the Matisse image. And we're doing the optimization with some gradient-based methods, like stochastic gradient descent, and go on. And okay, so sum up what we done here. So we define the loss functions for content. We define the loss function for art. Then we define total loss function for both. And what we are doing, we just compute the derivatives of this function with respect to the input data. So then we can update the input data, which is just this image with white noise, with these derivatives, to get new image. And then we perform gradient-based optimization for some iterations. And then what we get? This, which is pretty cool. Yeah. So this is how Mateusz would draw our CEO. Yeah, so we did this in Theano and Lasagne, which are Python frameworks. Theano is a library which has some bindings to CUDA. And actually Theano has also a very nice feature because it creates the graph of computation and has something called automatic differentiation. So we don't have to do the backpropagation on our own, and we don't have to compute the gradients on cards. So actually we forgot some analysis, unfortunately. But Theano is doing this for us in most of functions. And Lasagne is just a little bit high-level wrapper on Theano, which is actually quite low level. We computed this with NVIDIA GTX, and yeah, not Titan actually, in your computer. Yeah, but we usually use Titan, and Titan is awesome. So the repository is at this link at our GitHub, and I'm not sure if it is because I just pushed before the presentation. So if it's not, then I will push later. So here is a link about deep learning, which is very cool. There are many information about the papers, talks, tools, Theano documentation. And Theano is actually a framework which is developed by Lisa Lab from Montreal by Yoshua Benjo team. And it's pretty awesome. But for convolutional neural nets, the best framework is Caffe, which, yeah, it's the fastest one, has the fastest convolution. It's so it's coded in CUDA, yeah, in C++ on CUDA, yeah, from CUDA, yeah. And it also has, of course, Python binding, so we can do this because we are always coding in Python. Yeah, so I strongly recommend to try to reproduce the results on your images, because on the repository there are already pre-trained weights, and actually you just have to change some paths, because they're probably hard-coded because it was quick. Shit. Yeah. Yeah, but then it will work, just work, if you have NVIDIA GTX, because if you do this on CPU, then it's going to take like 1 month. Yeah, so this is everything. Okay, so here are some contacts to us, so you can write us. We are looking for people in machine learning, so everybody's welcome, and thanks.